Thank you for being here. I feel a bit tired. It was a good day, so I had to concentrate a lot, so I hope it will not be unbearable. So I'm going to talk about expanders and about monotone expanders. And I didn't know, before Alexandra started talking, I had a different introduction. I explained a few things. Now I wrote this slide. So expanders are graphs, and we have good motivation to study them, and there are a few ways to define them. And I will just start now with what I will call expander in this talk. It's a bit different because I will consider the bipartite case. So expander will be just a bipartite graph, such that both of its sides will have size n. There will be two sides, A and B, finite sets. And for every set on the left that is not too large, the neighborhood on the right is a bit larger. So this is the formal definition of an expander. I guess all of you have seen this at some point. And because they are so nice, we would like to understand expanders. So I will give some background about expanders and then say, what do I mean by understanding? So there are two basic questions. One is, are there expanders? And the other is, can we build expanders? And we know the answers to these questions. So Pinsker showed that most graphs are expanders. This was a long time ago. And as time passed, we also learned how to build these graphs. So the first construction was using group theory. And Margulis and Gaber and Galil showed that you can build a very simple graph. The vertex set is the torus, n by n, and the edges are defined by very simple affine maps, like x, y is connected to x and x plus y, and things like that. And this graph is an expander. And this follows because there is a big group in the background that has good properties, property T in this case. So it's group theory. Another construction, which is, I think, more delicate analysis somehow, is based on number theory. And this construction gives you take the cyclic group with p elements, and you define the edges by simple algebraic maps. So you can construct expander in this way. And so we have group theory, number theory, and there are also iterative ways to construct expanders. This is the zigzag product, for example, which basically takes two graphs that are expanders and builds a bigger expander. So we have ways to construct these graphs. And there are more. And I think a legitimate question is, how simple can these graphs be? So there are a few ways to answer this. So in some sense, they are very simple because basically all the graphs are expanders. Another statement which Ungar proved is that expander graphs cannot be planar graphs, so they are not too simple in this way. Another statement that Clave proved is that you cannot do a one-dimensional construction that is analogous to this Margulis two-dimensional construction. Maybe I will talk about it in the end, a little bit more.
What do you mean affine maps?
Yeah, you can't do a one-dimensional construction using affine maps, or even slightly more general statement. Maybe I will talk about it at the end. So they cannot be too simple in this sense. Another meaning of simple is, can you put them in a book with few pages. This is a, I will define this formally in a bit. So this is another way to address the simplicity. And the last question is, do we have monotone expanders? And both of these notions I will now define. So I will start with defining these constant page graphs. So a constant page graph, you can think of the vertices as being on a spine of the book. Spine, I think it's called. And you can think of the edges as drawn on the pages. So here I drew the edges on one page. And the restriction is that the drawing is like this. The edges are not allowed to cross each other when you draw them. So this is a one-page graph. This is a two-page graph. So you can add more pages to the book, and you get constantly many pages. It's clear?
They're nested or they can be two circles within one.
Yeah, they don't have to be nested.
Oh, okay.
No, yeah, you can have another edge here if you want. Yeah. So these are constant page graphs. These are simple graphs because they fit in a small book.
Some generalization of planarity.
It's some generalization of planarity. This is right. And another motivation to study these is they are related to some Turing machines and their simulations. I will not talk about this much or at all. So these are constant page graphs. So this is a simple family of graphs. Another simple family of graphs is monotone graphs. A monotone graph will be, in this talk, a bipartite graph again. So now, again, we have two sets. But now these two sets, you can think about these two sets as integers from 1 to n. And the integers are ordered. 1 is smaller than 2, and so forth. And you can define the graph, or the edges of the graph, using D-monotone maps. So these maps need to be monotone, so they respect the order on n. And if you try to do a full a map that is defined on all of A that is monotone, there is only one, or basically one such map, which is the identity map. Otherwise, there are collisions. If you want strict monotonicity, so you may allow them to be partial, so they are not necessarily defined on all of A, but just on some subset of A. So here is an example of edges defined by one monotone map. This is A, this is B, and these are, say, if 1 is mapped to 2, 2 is mapped to 4, and so forth. And you can add more layers. So this is another monotone map. Each layer separately is very, very simple, but the overall structure can be fairly complicated. So these are monotone graphs. They are a finite union of simple matchings. Okay, so we have constant page and D-monotone.
So in this definition, monotone can be either increasing or decreasing, so, right?
So the definition is like this. If you have, if x is smaller than y, then
But
f
it
of
can
x.
be either increasing or decreasing, because in this definition it has to be increasing, right? It doesn't make sense.
Yeah, yes.
It's not interesting, right? You just said the next bigger guy is mapped to a bigger element.
But in that case, the vertex number n can be mapped only to n, right?
No, just bigger than the
But
previous.
it's partial.
No, it could be mapped to n over 2, for example.
Ah, okay.
Yeah. This is the reason to allow the partial.
Okay.
Yes.
Okay.
Good. So, simple observation is that monotone graphs are constant page graphs. So here is this was proved by Zeev and Avi. And it's if you draw it, it's fairly simple. You put here a monotone graph, and here a page graph. So what happened, this moved here, and the upper side moved to the right, but was flipped. So this matching became this thing, and this matching became this thing, and we have now a two-page graph from a two-monotone expander. So this is general. So page graphs are more general than monotone graphs. And what I will try to tell you today is how to build these monotone graphs with a constant degree, with a constant number of generating functions. And as a corollary, as we said before, there are also constant page graphs. And maybe I would say one way to try to build these graphs is to take random graphs. Random graphs are good expanders. Maybe take a random monotone graph, it will be a good expander. It's not completely clear what does a random monotone graph mean, or it could mean many things. But if you take some natural distribution on a random matching, just one matching, then it is quite close to being a linear map. Every point is mapped to some, say, every x is mapped to 2x, roughly, or something like this. So natural distribution give you maps that are close to being affine, and such graphs cannot be expanders. This is what Clave proved. So I don't know of any probabilistic construction of these graphs. And if you want to do this, it requires some clever choice of a distribution. And another comment that is maybe related a bit to motivation is that from monotone expanders, you can get another object, which is called dimension expanders. So do you have questions? You're very quiet. Yeah, I will do it in the next slide. Yes.
If this is log n, is it easy to get?
Yes, this is this already Dvir and Špilka. They built a dimension expander, but it was actually a monotone expander. So
For
yes,
D was log n.
yes, for D log.
So who introduced these things?
So as far as I know, this started with these dimension expanders actually, which I will define in a bit. And I'm not sure who actually asked about these things.
Yeah, so some attempts, well, it doesn't matter. We have some with Amir Špilka, and there we asked this question, and eventually we gave it up. And Dvir and Špilka implicitly defined shoulder reduction to monotone expander, and again sort of made it explicit.
Yeah, in their paper, Zeev and Amir Špilka implicitly used the notion of the monotone expander, and later Bourgain observed that this is actually the property they used, and this was the way it was defined. So, okay, so I want to explain what are dimension expanders. These are, in short, briefly, they're a generalization of expanders. In what sense? So here we will have some vector space. F is any field. And you look on the n-dimensional vector space over the field. And we want to find a constant number of linear maps, L1 up to LD, from the field, from the vector space to itself. And you can think about them as being invertible n by n matrices. And you want the property is that if you choose any subspace V of f to the n with not large enough dimension, then if you apply all of them on V, you get few vector spaces. You take all of them together, you get slightly larger dimension, plus some absolute constant. So this is a dimension expander. It sort of generalizes the notion of expander in some way, but it's these matrices are not necessarily graphs, so it's not directly expanders. But it's a natural generalization somehow.
Gadgets like this?
The optimal one, I have no idea.
There is an alone Bofan, analog alone Bofan.
I don't know.
Well, it's okay, there is a spectral gap.
Um,
It's not clear that there is a, if you are doing it over the real, then you can define notion of spectral gap. If you are doing it over a finite field, this definition is interesting over any field.
Here you measure the dimension of the reunion. It's a strange, I don't know, but it's not clear to me even how to define it now. Okay, so there may be optimal.
The definition is to define it so that one of these maps moves the vector space to one with smaller intersection, with 1 minus 3 times the dimension of the intersection. And that's completely analogous to what happens in normal expansion.
So yeah, you can ask what is the given D, what is the maximal C you can achieve, and I don't know the answer. Or 1 plus C. It depends how we measure. Okay, so these are dimension expanders. And I want to mention that over the real numbers, Lubotsky and Zelmanov showed that basically many construction of real expander graphs, not dimension expanders, that we know actually yield dimension expanders. And no, it's related how you build the expander. So it doesn't.
The definition Avi said, is it possible to construct such a thing?
What is?
Where you just need to act by one subspace to increase, like for every V there exists a single Li which increases the dimension?
It's equivalent if D and C are constant. You just. So over the real numbers, we know of such things, and the observation that was implicit in Dvir and Shpilka is that if you have a monotone expander, you can very easily build from it a dimension expander. I will not explain this, but it's very simple. It's an exercise, simple.
These dimension expanders, the random sets of linear maps have this property.
Yes, yes. The question is about construction.
Yeah, but I mean, I guess maybe the natural notion of a Ramanujan one would be what's...
to achieve the random one. Yeah, yes.
What is C for the random one?
No, I don't. You know? No?
It may depend on the field. Yeah, but it's true for every field that random ones are good, like 10 random maps will give you something.
Okay, so we defined what are D-page graph, monotone graphs, and monotone expanders, and these dimension expanders. And now I want to try to explain how to build these graphs. And we will have 4 parts to the presentation. First, I will say what are Schreier diagrams. These are ways to define graphs from group actions. Then we'll discuss a continuous version of an expander. This will be useful for us. Then I will tell you exactly what are the choices that are made in the construction, and then I will try to explain a little bit about how you prove this. Okay, so let's start by the basic object. These are Schreier diagrams. So a Schreier diagram is a graph, and it represents the action of a group G on a set X. And there is some finite subset of the group that we choose, and they will define the edges. So a group action is familiar. So the way you define it, it's very simple. In this case, I will make it a bipartite graph. So on both sides, you put the set X on which the group G acts. And the edges, you connect a point X to a point G of X, where G is some element of S, or if S is symmetric. So this is a very natural way to visualize an action. You just draw what it does. And so here is maybe a more familiar notion is Cayley graphs. This is when G acts on itself. Then it's called the Cayley graph. And here is an example of a Schreier diagram. So the group will be a group of 2 by 2 matrices with determinant 1 over a finite field. There are roughly p to the power of 3 elements in this group. The finite subset will be these 2 matrices and also their inverses. And the action will be the Mobius action on the line, which is the line has roughly p points on it. And this is the way the action is defined. It's called the Mobius action. The point x, when you act with a matrix G of this form, is mapped to this point. And if you divide by 0, you get infinity and vice versa. So this is indeed a goof action. I will not prove it now. So now we get a graph. What is this graph? It has roughly, the size of the graph is 2p plus 1. On the right-hand side we have p plus 1, and the right-hand side we have p plus 1. It's 4 regular. We have S of size 2. So the graph, in the graph you don't see the group where it came from. It's a smaller object, but the group is much larger than the graph. It's of size p to the power of 3. So here, this is an example of a Schreier diagram. So this is the first part. What are Schreier diagrams? It's clear? Yes? Take it as a yes. The next part of the construction is what are continuous graphs for us. So a continuous graph, it will be exactly the same as usual bipartite graphs, but the set of vertices will be the interval 0, 1. And now the maps are maps defined over the interval, so they will be very smooth, as smooth as you want, and monotone with respect to the order of the interval. And there will be an expansion property. The expansion property is with respect to the Lebesgue measure on this interval. So it's exactly the same, except that instead of n points, we have more points. Okay, so this is clear. Good. So this is a continuous monotone expander. And why is this thing useful? It's useful because of the following simple observation. If you take the interval 0, 1, this is 0, 1, and partition it to interval of length 1 over n consecutively, then you can round the continuous object to a finite object. And if the continuous object is an expander, also the finite object will be an expander. And this is the way you do it. Say you partition the left-hand side to this n interval and the right-hand side to this n interval. And you connect interval aj to bk if the map C of I acting on A of j, this is, say, an interval on the right-hand side, intersect the interval bk. So you just do the natural thing. You look what happens here. If it touches, you connect I and j in the discrete object. So it's simple to see that if the original thing was an expander, this one is also. Um,
I've been
yes.
missing something very stupid, but these smooth maps, they do not have to have gradient at least one, do they?
They do not have?
They do not have to have gradient at least one, or they do?
No, they could be shrinking also.
Well, surely then you could have an interval on the domain, on the target side, bi, where many different intervals end up hitting the same interval because they all got much shorter.
Yeah, that's correct. But the point is that these maps are smooth, so you can take an interval of length 1 over n and blow it to an interval of, say, 10 over n, but the degree will be still constant. Do you see what I mean?
How do you get constant degree? I don't see that.
Yeah.
So you just have, when you have monotonicity, you have weak monotonicity. You don't have strict monotonicity in this construction. So it could be that x is less than y, and they map to the same point.
Yeah, that's correct.
Right. But your definition of monotonicity before was strict monotonicity. So I think that might be...
But yeah, if a few points hit, like if 10 points hit, 10 edges hit the same point, you just take 10 different edges. You just split it even more.
But they're still all hitting the same point.
Yeah, but they are on different levels.
But then you get more levels, though.
Yes, but only a constant.
How do you know it's a constant, unless you bound the derivative?
You bound the derivatives, they are smooth. Yeah, they are smooth. It's a compact domain. Everything is like nice, no... yes? Okay. So this is why this is useful, and how now I want to explain how to build this. So how to build this continuous object. It will be similar to the Schreier diagram from before, but it will be slightly different. Here the group will be SL2R, real matrices now. And we need to find a finite subset of this group. There are many choices that could work. The choice, a choice that works is you look on these three matrices. You look at words of constant length, say 1 billion in these three matrices. And this is the set of generators. So it's a constant subset of the group. And the action is the Mobius action. It takes a point x in the interval and maps it to this real number. There will be no infinity in our case. Everything is close to the identity.
R is much smaller than K and Q.
It doesn't really matter also. But yeah, you can choose it to be smaller. But you need, so this takes a point in 0, 1 and maps it to some other point. And we want to make it, the image to be 0, 1 as well. So to do this, we truncate this map to be a partial map. Instead of being defined over all of 0, 1, we take the pre-image of the interval 0, 1. So we get a subset of 0, 1, and it became a partial map instead of a full map. Is it clear? Good. So this is the construction. Maybe, so I will summarize this. This gives you a continuous monotone expander. And as we said, by this discretization procedure, we get also discrete finite monotone expanders. And maybe some comments about this. So the first comment is that all of the constants here are crazy. And the degree is very large, the expansion is very small. There is no control on these things. And another comment is that I said that this is a monotone expander. So far we just saw that it defined a continuous map. And this action is monotone because the Mobius action is monotone. So this is the Mobius action, this function. And it's well known that this is a monotone map, how do you prove that something is monotone? You just take derivative and see that it's positive. So you just do this, and because the determinant is 1, it becomes positive. So these are all positive maps. So at least we know it's monotone, but now we also want to know why is it an expander. So this will be... so let's talk about why is this an expander. So Peter Sarnak thinks about it as the proof has 3 steps, and he thinks about it as 3 steps of a chess game. And the reason to think that is that every step of the proof has a different objective. Like in every step of a chess game, you have a different objective. And these 3 steps were described by Bourgain and Gambourg. I will state exactly the results later, who took some result of Helfgott, and I will explain how the ideas flow later, like in the next slides. And now I want to say in briefly what are the 3 steps. So the first step, the opening step, is to say that locally the graph is a tree. The graph we are considering locally is a tree. It has large girth. This is the first step. The second step is to prove something about the group. It's additive combinatorics. And the third step is to use some mixing property of the group, or in this case, of the action. So these 2 things will be statements on the group, and the last step will be a statement, in this case, about the action. Okay, in this case, we will not be able to. In other cases, you are able to do the mixing property in the group itself. In this case, the group is too large, but the action is nice enough that you can argue about it, and I will explain why. So these are the steps. You first show it has large girth, then you show some product growth in the group, and then you use some property of the action. Okay, so I will explain these 3 things now. So first, large girth. In this case, large girth comes from what is called the Tits alternative, or the effective Tits alternative, that all of these people contributed to. And it's this statement. There is a constant R, a number like 1,000, so that whatever subset, finite subset of SL2R you take, if this subset generates a group that contains SL2Z inside SL2R, then in words of length R in S, R is independent of S, there are 2 elements in the ball that generate a free group on 2 elements. Okay, this is the Tits alternative. And the key point is that R is independent of S. This is the effective Tits alternative. I will not say anything about the proof of this, except that we need a slightly stronger version, which is actually a corollary. What is the slightly stronger version? It replaces the 2 with some number k. So there is some constant R, so that for every k, and for every subset S as before, if we look at words of polynomial length inside in S, we can find k elements that generate a free group. So how can this be a corollary of this? Basically, I think the only way that I would say it's a corollary, if this argument has nothing to do with SL2. It's just a statement about F2. Inside F2, you can find you can do this. So maybe I will. Yeah. So this is it's a nice way. It's a nice game to find these k elements in F2. It's not difficult. So this is the first part. This is a deep theorem that uses the pinpole lemma in projective geometry. It's deep.
But you only need this for those specific matrices.
Yes, you're right. Yeah.
Does it require the full strength of all of their arguments just for those matrices?
No, yeah, you're right. They prove something much, much more general. And I think that in this specific case, even just for SL2Z, you can do better. You can use simpler arguments. And I think Tzachik Gelander has some note about this specific case somewhere.
From this point on, you will just use the k elements and you forget about all the others, or expand.
Yeah, I will actually not say exactly. So this is the first part. I will not say exactly. So this is the first part. We found these k elements. Maybe I want to mention that we don't know what are these k elements. What I wrote here is like abstract thing. If we want this to be explicit, what do? We just take all of these k to the r things. We don't pick them in a clever way, and they just make it even more expanding.
But the argument will use a large girth, which doesn't hold for this k to the r. So
Yes.
You're really talking about the subgraph that, what will you do? Will prove expanding it just what's spanned by the k.
Yes, you're right.
Exists.
You're right. So in the choices, we take all of these things. In the proof, we argue just about these k things that we do not know what they are. So this is the first part. The second part is a product growth in the group. And this is the slide I will have on this. So it says that if you choose a subset A of SL2R, and this subset should satisfy some technical conditions that I will not talk about. It has to have some nice behavior in many scales. And then if you multiply A by A 3 times, you pick 3 random elements of A and multiply them, this set becomes larger than A. And the way to measure size in this is the metric entropy. So this is the main technical part of the proof, to prove this for SL2R. But this continues a very fruitful line of work that has 2 parallels. One is in the finite field case that started with the sum product theorem, then work of Helfgott, and then Bourgain and Gamburt made these 3 steps that we call chess game. And they also, there is also a real analog of this, where the sum product theorem becomes this theorem. It's a theorem, although it's called a conjecture. And then they use this to prove expansion inside SU2. The main difference is that this group is compact. It makes things easier. And SL2R is not compact, so there are more technicalities to take care of. So this is the second part, the product growth part. And the third part discusses the action. And I will not say exactly in the real case what happens. I will give an example in the finite case, which is contains all the ideas. So here, assume that G is a finite group and it acts on a finite set X. The mixing property is what is written here. You can think about mu as being a probability measure on G. and of f as a vector that is orthogonal to the all one vector on x. So mu is on G, f is on x. Then you can look what happens when you convolve mu and f. So you take averages. F of x is the average with respect to the action. So this is the formal definition of convolution. And the requirement is that the convolution, its two-norm decreases. If you remove the n, this is Cauchy-Schwarz inequality. And what this property tells you that you gain over Cauchy-Schwarz. If n is large, so this is useful when n is large. Okay, so mixing property is this property, and it's useful when n is large.
What is n?
N determines how good is the mixing property. It's unspecified. Yes. And this was used in many works, this idea. So this is a short summary of the definition. So it was used in all of these things, all of these works, and also when David talked, he also mentioned this. So this property holds when the group we look at has only large dimensional irreducible representations. This is one example when this property holds. Another example where this property holds, and it's actually simpler to argue somehow, is that if the action we look at is just too transitive, so it doesn't talk about representations at all. We just look on the action and we require it to be too transitive. And this is, it's fairly simple to do this. You do Cauchy-Schwarz once and it just happens. And in this case, we are very happy because the Mobius action that we used is actually free transitive. So we are able to perform this step to argue. And this, because SL2R is not compact, it also becomes messy, but this is the basic idea. So this is the third step. You use that the Mobius action is free transitive. Okay?
Can you say what you achieve at the end of each step? I mean, is there some...
Yeah, I wanted to discuss it, but I think I prefer to mention an open problem, and I'm also running. It's not complicated, I can tell you. So these are just ideas on the proof. So here is what we said so far. There are simple expanders in this sense. There are monotone and also constant page. And to prove it, we used many things. And we discussed this at least in some detail. And I want to mention one question that is related to this. So this is the last slide. So here is the question. The question is, are there even simpler expanders? Simpler, even monotone expanders? So here is a natural candidate for building an expander, a graph, sorry. So the graph will have the left side, both sides will be the numbers from 1 to n, from 0 to n minus 1. And we map a number x to a number aix plus bi, but this number may not be integer, so we first round it to an integer and then take modulo n. Okay, so this is a map from 0 to n minus 1 to 0 to n minus 1, and we can ask ourselves, can we build expanders using such simple maps, just affine maps? And what Clave proved is that if we just use here rational numbers, then we cannot build expander graphs. And I want to mention that when you act with rational numbers here, it's not an action. There is 1/2 times x it's not x over 2 in Zn. It's something completely different, or it may be completely different. So these maps do not fit into the action area.
Can you repeat this? I don't know. What do you mean divide by 2 is not the same as?
If you say take
It's over
x,
the reals, the computation is over the reals.
it's 1/3 instead of, so this is 1 over 3, this is 1, and 3 inverse modulo n, this is a different number. So
And in this theorem, the AIs and BIs are fixed, and the family is as n varies. That's
yes, here we choose AI and BI to be, first we choose a constant number of rationals, and then we try to use them to build an infinite family. And what is the reason that this theorem holds? It's a simple reason, and the reason is that the one-dimensional affine group is solvable. So this basically holds for all solvable groups, but only for rationals. And the main question is that is very interesting, I think, is what happens for real coefficients? Can we build expanders using such schemes when the coefficients are real instead of rationals? It seems like a very subtle, like, why should it matter? So I want to mention two things. One is you can make here the statement of Clave a bit more general, and this uses Diophantine approximation, very simple Diophantine approximation, but it also sort of shows why R is interesting, because you need to really control the behavior. And another comment that if you replace solvability by polynomial growth, which is a weaker condition, or a stronger, yeah, it depends. Yeah. So every group that has polynomial growth. Yeah, yes. So if you try to do it with real groups of polynomial groups, not rational, real groups of polynomial group, like the Heisenberg group or some other thing, then you can also not build expanders, and this is it's simple. It's not. So for polynomial groups, this doesn't work. But for solvable groups, I don't know if it works. And any proof of it should distinguish between R and Q. Should use something more more deep. Or I don't know how to phrase it. So I thank you for this attention.
Questions?
Yes.
Can you say now what you're trying to achieve at the end of each phase? I promise it was easy. Explain.
So I can try. So let's ignore that this is a continuous space. Let's just think it's finite. So in the first step, we just argue that the graph locally looks like a tree. So this is step one. So we start with a random walk from a point and see what happens to it. So in this time, it behaves perfectly. It's an expander. Now we reached a fairly large subset of the graph. From here onwards, this set, when you multiply it by itself 3 times, you get a larger set. So multiplying itself by itself 3 times corresponds to taking this 3 times. This 3 is defined by S. So after a constant number of steps, we reach a very large part of the graph, almost all the graph. So this is part 2. In applying squaring a constant number of times, we reach even not like n to the here we are at size 1. Here we are of small size. Here we are basically everything. And from here onwards, to get to the whole graph, this is the mixing. This you get from controlling the convolution. So in one more steps, you get uniform. This is a rough idea. I hope it was somehow clear. Yeah, it was. You want to?
But this is maybe a stupid question, but if you, what if, in the question you asked here, what if you set bi equals 0 and also just remove the leftmost portion of the interval? So you just want to get n over 2 up to n to expand under maps of the form integer part of aix. So
if you allow, if you want to focus on the left part, it's easy, yes. Because it's also in the, if you look on the map, x maps to 2x, it's an expanding map. So it's expanding here, but here there will be something that doesn't expand.
I see, so somehow the whole point is you have to have the whole interval.
Yeah, you need to take care of the whole thing. This is somehow related to what happens after you make this map unitary, when you divide by the derivative and in the group language.
Did you guys try like iterative constructions?
Avi and they have an iterative construction in the zigzag flavor, and it works, except that you need something to start from. And the only thing we know to start from is this thing. So actually, after you know this thing exists, you just look inside the graph. Say you want to construct a graph of size n. You look in graphs of size log, log, log n, something like this. You find the best graph there is. Then you use zigzag and you get everything, right?
So yeah, so you can start from scratch, but the degree would be any iterated log you want, but not.
You need a growing power.
Yeah, it's a problem, like you said, with the base.
You need to know that there is an infinite, a dense enough infinite family of these graphs. Thank you.